All right, next thing we're going to look at is atom effects, right? So what atom is holding on to that H plus? Is it likely to donate that H plus, or is it not likely to donate that H plus? So let's take a look at an example. So here we have HCl, and this is a strong acid in water. And so it likes to donate this H plus, right? H plus plus Cl minus. And if you think about your compounds, chloride is very electronegative atom. It's actually also a very large atom. And so this is relatively stable. And so since this side is stable, it's okay donating its proton and just hanging out as Cl minus. On the other hand, we have CH4, which is a very weak acid, or not an acid at all, you can think about. And so if you try to donate its H plus, you'll end up with CH3 minus. And so carbon is not a very electronegative element, and it's not very large either. And so it's relatively unstable. And so since this side is unstable, it's going to much prefer to hang out on its CH4 side. And so there's two main factors that stabilize negative charge. And which one is important depends on which two atoms you're comparing. So the first thing is size. And then the second thing is electronegativity. And when it comes to size, bigger is better. So the bigger your atom is, the more better it's able to stabilize this negative charge. And this makes sense because that negative charge is spread out over a wide area, right? If it was squished into a tiny area, negative electrons are going to repel one another, and so that's going to be very hard to keep stable. So the bigger it is, the better. And then electronegativity, the more electronegative, the better it's going to stabilize this negative charge as well. Remember, electronegativity is the measure of how hard it's pulling on this these electrons, right, this negative charge, and so it makes sense that a higher electronegativity would be better. And so if we take a look at our elements, we've got carbon, nitrogen, oxygen, fluorine over here, and then under it, phosphorus, sulfur, and chlorine, and then bromine and iodine. And so it depends how we're looking at this. So when we're going from left to right or across a period, electronegativity is going to dominate. So when we're going like this, left to right, we're thinking about electronegativity. So the more electronegative element is going to be more acidic. So HF is going to be more acidic than a CH bond, right? And then when we're going up or down a group here, so when we're going up or down, what's going to dominate is size, right? Size. So when we go down the periodic table, we get bigger. And so you may be thinking, why do we have these two different trends? Why doesn't one dominate the other? Well, it's a question of how much do these things change. When you're going from left to right, your size doesn't change that much. Your carbon is 67 picometers. Your fluorine is 42 picometers, right? That's not that big of a difference in terms of size. But when you're going up and down the periodic table, the size difference is quite significant. So for example, fluorine is 42 picometers, while iodide is 115 picometers, right? So iodine is more than twice the size of fluorine. And so the size effect is bigger when you're talking about going up or down a column, and not so big when you're going left and right. And so since it's not so big when you're going left and right, it's electronegativity that dominates. So again, when we're talking about across a period, electronegativity is the factor that you want to consider. And so for example, carbon, nitrogen, oxygen, right? When we go to the right, we're more electronegative. But in terms of the size, it's actually towards the left is bigger, right? But the one that factor is going to win here is electronegativity, because we're talking about going across a periodic table. And so we can think about, carbon with a negative charge, nitrogen with a negative charge, and then oxygen with a negative charge, right? And so these could all be bases, so they could be turned into their neutral components by gaining an H. And then if we think about the stability of these compounds, this has a negative charge on oxygen, a very electronegative element, and so that this one's going to be the most stable. Whereas over here, we have this negative charge on a carbon, a not very electronegative element, and so this is going to be the least stable. And so since this thing's stable, right, it's not going to have a lot of pressure to pick up an H+. And so what that result is this is going to be the weakest base, right? It's okay just having that negative charge. And since that's the weakest base, this alcohol here is the strongest acid. Whereas on this hand, right, this negative charge on this carbon is very unstable. It's very unstable. It does not like to be like this. And so it's going to want to pick up an H+. So this is going to be the strongest base, right, which makes this component right here the weakest acid. So when you're thinking about how strong one of these acids are, you want to think about how stable is their conjugate base, right? And you can tell by the pKa's here. So the pKa of this guy is 50, this one approximately 38, and then this one 16, right? So we get more stable or more stronger acid as we go to the right. But remember, these must be the same charge if you're going to compare them. So charge is always the number one factor. So for example, if you have a protonated nitrogen versus just water, neutral water, the positively charged one is going to be the stronger acid. So charge wins first, and then after considering charge, if they're both neutral or something like that, then you want to consider atom effects. And so then when we go down a group, size wins, right? So for example, we have oxygen and sulfur. They're in the same column. Even though oxygen is more electronegative, that's not the important factor here. The important factor here is size, and sulfur is bigger. And bigger is better because you're spreading this negative charge over a larger area, which is more stable. So for example, if we had water versus H2S, right, you can see these are pretty similar compounds. The only difference is oxygen or sulfur. If we try to deprotonate each one of them, OH minus, we'd get, and then SH minus. This SH minus is more stable, right? It's more okay holding that negative charge. And since it's more stable, it's not really going to want to pick up an H+, which means this will be the weaker base. And since that's the weaker base, it must have the stronger conjugate acid. And so these kinds of things are just really easy to get mixed up in your head. Just do some practice problems, and then you'll start getting it.